All right, so first I apologize, my talk has migrated slightly off of what I was initially planning to talk about, but I do touch on that in it, so if you're excited by the abstract, I do touch on that. I ended up coming up with a new idea to describe something that we've talked about and Adam touched on earlier today. And what I'm calling it is the attacker-defender ratio for password algorithms. What this involves is starting with the defender, whoever is the legitimate user of passwords and the hashes. We give them a computer, and this is typically going to be a web server or something along those lines. We find out how fast they perform their hashing algorithm, and then we set this as the sort of the 1x or the default speed. Now, as many of you know, given an identical computer to the attacker or to the defender, the attacker is, in many cases, able to perform the tests on the passwords rather substantially faster. And this depends somewhat on the hardware, but John the Ripper typically outperforms a web application with PHP in cracking things. If you throw GPUs into the mix, speed up factors of 100 times or even greater are possible if you're, say, running your web server on Jeremy's box with 8 GPUs in it or something. And so what I'd like to explore is how we can basically make this ratio better and reduce the speed up of password algorithms. And I have a number of thoughts on this topic and some algorithms that I'd like to point out as rather spectacularly bad examples of this. The first thing that really matters is hardware. Typically the defender, whoever your web server or corporate authentication server or whatever else, it's typically running some sort of x86 or possibly ARM CPU, depending on the data center. You typically have L1 cache and L2 cache in the system, although we don't make great use of that. You also typically have a vector engine. Pretty much any x86 or ARM CPU in the data center at this point has at the very least SSE or on the ARM side, the Neon extensions. And so that's what the defender has. The attacker typically has really the same hardware available to them, except they get to choose their hardware. So they may have a more advanced vector engine than the defender. And then it goes downhill from there because the attackers anymore typically have GPUs, and as many of you know, lots of them. It's not uncommon to have an 8-card system, and with VCL and the clustering work that's been done lately, 20, 30, 40, 50 GPUs attacking a single problem is entirely within bounds and fair. The attackers also have the possibility of using FPGAs, should they decide to do so. It's not very common right now, but there are certainly companies selling FPGA accelerators. And finally, the attackers could, if they wanted to, use ASICs. I don't actually see this as terribly likely, simply in that by the time you get to developing ASICs for the password algorithm, it's probably not the weak point. There's probably easier ways to get what you want than building a giant ASIC farm to crack passwords, but I could very well be wrong on that. Unfortunately, with the state of algorithms today, it gets worse because most of the hashing algorithms used today don't make any use of the memory system. So they're not using the L1 or L2 cache, and they're not typically using the vector engine. So really what we've done with all of the MD5 and SHA-1 and all of the other storage algorithms, even the complicated ones like PBKDF2, we've effectively set up password storage algorithms where the attacker has all the benefits. They get the same hardware, except they can use its vector engine, they can use the GPUs, and they can use as much hardware as they would like. So hopefully this will get resolved, and if people are not aware of the password hashing competition that's going on for algorithm design, I would suggest taking a look at it. I don't remember exactly what the website is, but
PasswordsCon.net.
okay, it's apparently, is there a hyphen in the middle?
Yeah.
Okay, so it's password-hashing.net. Take a look, and if you have ideas on how to make things better, please submit a proposal. So one of the things that I'd like to mention as well, and this applies to both CPUs and GPUs, memory access patterns make a big difference. Doing a sequential read through memory is incredibly fast, and especially when you look at video cards, if things are properly arranged in memory, they have hundreds of gigabytes a second of bandwidth, and they're not afraid to use it. One thing that we're seeing a little bit, but not nearly as much as I would prefer, is random memory access patterns. Because this really plays to the strengths of the defender in that they have their L1 and L2 cache, which are designed specifically for this type of access pattern. The attacker, on the other hand, is typically limited in how much high-speed memory they have. They won't have that much shared memory on the GPUs. And if you can force the attacker to do something like a random access pattern in global memory, you've pretty much won against a GPU. And even on the CPU side, if you're forcing them to spill into L2 cache and the main system memory, performance drops substantially, and so you've reduced the advantages that the attacker has. The other thing that I'd just like to mention, and this is probably fairly obvious to anybody who's gone playing around with password tools in the last decade, vector engines are awesome for password cracking because they let you load up a whole bunch of 32-bit values into a 128-bit or on newer CPUs, even 256-bit wide registers, and do all sorts of work at once. Again, right now, we're not making use of that on the defender side, and we really probably should be because they have the hardware for it. Right there with SSE, you've given the attacker essentially the 4x multiplier in performance over a defender who's not using vectors. Off to something completely different because this didn't really fit in anywhere else. One of the questions that I've occasionally received is how do you rapidly see if a candidate hash that you've generated is in a list of the 1 million or 2 million or however many hashes came from the latest dump. And one of the most efficient ways to do it is to use a bitmap. And specifically multiple tiers of bitmaps where you have them basically giving you a definite no if on the candidate. So it's a neat little trick, and I'm assuming Adam does something similar. I think John Liver does something similar as well. And that's a neat little way of speeding up your hashless lookups. So now, on the attacker-defender ratio, I did say I had some case studies, and Adam did touch on one of them earlier, but I'm going to dig into it a little bit more. One thing that's very important to understand with MD5, SHA-1, and all of the other algorithms is that they work in blocks. They take a block, which is typically 64 bytes of data today. They add some padding to the end of it, usually encode the length band, and then they process it out. If any of you have ever wondered why there's a 55-character limit in most password cracking tools, this is why. That's as many bytes as you can put in a single block of an MD5 or SHA-1 operation. When you have more data than that, what happens is the initial data, or the initial state is loaded. The first 64 bytes of data are processed through the algorithm, and then you get the state at the end. You take that state, you process the next 64 bytes of data, and you get another state. And you keep doing this until you get your final hash. What specifically matters about this for passwords is the state at the end is simply the state at the beginning of your block plus the data that you're hashing. All of this other stuff just gets condensed into one single state, which is typically right now the output size of the hash for things like MD5, SHA-1, etc. So there's two algorithms that I'd like to point out that are, as probably won't surprise you, web-based algorithms that really kind of do it wrong. The first one is IPV, which Adam did talk about earlier. And this is, you take the MD5 of the password, you concatenate the MD5 of the salt, and you take the MD5 of the entire thing. The second one, I actually don't know where it came from, but I did implement this for fun because someone asked me to. It is clearly the result of somebody who decided they needed to put more MD5s in their password hashing algorithm. So they take the MD5 of each individual character, they concatenate that together, and they take the MD5 of the result. If any of you wrote this, please don't tell me. So the first thing that I'd like to do is dive into the IPV algorithm a little bit more. For the defender, for the unlucky forum that is stuck with this algorithm, they start with the user's password and salt out of the database. They then perform two MD5 operations, converting the password and the salt into the MD5 hash of that. And because it's web software, of course, MD5 comes out as a 32-character lowercase numeric string. They then take those strings, concatenate them together, and because this is a 64-byte long series, the padding and the length actually go in their own block, and so you get the final hash. So for the defender, they've had to do 4 MD5 blocks to get the final hash. The attacker, on the other hand, is typically running in a slightly different environment. They typically have a large list of unique salts and hashes. Very rarely do you go, man, we hacked the forum and we got one hash out of it. It's usually hundreds of thousands or millions or some very large number. Another thing, and this is one of the big weaknesses, the MD5 of the password is constant for all of the unique salts. And then the MD5 of the salt is constant. So what we can do as the attacker is go, well, instead of calculating the MD5 of the password for each password salt combination I'm trying, and instead of calculating the MD5 of the salt each time, we just do the password once until we change passwords. And we just calculate the MD5 of the salt on load. And so what this means is that when IPV wisely went from a 3-character salt to a 40-character salt, they didn't actually really accomplish anything. They could go to a 1,000-character salt, would still hash it once, and go. So what the attacker ends up doing is they have the password that is pre-hashed. They have the salt that is pre-hashed. And they simply do 2 MD5 block operations to get the final result. But it gets even better because Adam was talking about some of the zero optimized stuff. The second block, because they've managed to entirely fill the first MD5 block, the second block contains entirely static data. It contains a padding bit and the length, which is always going to be constant. So you can actually skip some of the work on that block and not have to do a full MD5 block. So, yeah, we've successfully made it easier for the attacker. If the attacker is not using a vector engine, they have roughly a factor of 2 speed up. You can go a little bit on either side, but it works out to about a factor of 2 speed up to do the same thing. If you throw vectors in, if you just throw SFC in, it's about a factor of 8 speed up. And if you throw a bunch of GPUs in, well, it just kind of depends on how many GPUs you have, but it's really, really fast, and this is probably not what the authors originally intended. So let's take a look at the next one. Let's take a look at this bizarre construct. As I said, I have no idea who created this. I don't know why they created it or what it's used in. I really don't want to. However, I do know with fairly high confidence that it was created by a web developer. And web developers, guys, I love you. Please stop inventing password hashing algorithms. But the output of the inner MD5s is 32 characters worth of ASCII instead of a 16-byte output. And this is what you get off the default MD1 functions in your web languages, PHP, Ruby, Python, whatever the web language of the week is. And so that's a good indicator that whoever put this together was using it for something web-based. And yes, it is really very silly, and I'll show you why. So, this is kind of what it ends up looking like. You do end up doing a lot of MD5 operations for it if you're doing it the intended way. Because for each character, you have to do the MD5 of that particular character. And then because the output is 32 bytes long, you can fit two characters into each 64-byte MD5 block. And then at the end, you've got your padding and length. So the defender who's doing this, who's going, man, look at how many MD5s we have to do. Isn't this awesome? Has to do n plus 1 divided by 2 MD5 blocks for a length-end password. Now, some of you have generated this table in your head already, but that's okay. If you haven't, I have it for you later. The attacker perhaps is a bit more intelligent and realizes that the MD5 of A is always the same. And so we create a table and we do the math and we determine that we only need 8K worth of data to store the MD5s in expanded ASCII form of every single possible input byte to those inner MD5s. So we don't have to do them. And so we get a bit of an improvement in that now we've eliminated that initial, the initial N MD5 operations. So for those of you who don't like doing this math in your head, here's a table. Here's the kind of the easy method. We've got better than a factor of 2 improvement. We're coming up on a factor of 3 improvement for length 9. But wait, there's more. It gets even better. Remember what I was saying earlier about how the only thing that matters in an MD5 or other hash operation is the state at the beginning and the new input data. If you do something intelligent with how you're iterating your passwords, you can end up with just changing the last block. And so if you just change the last block, you can skip having to recalculate all of this and just have to calculate the last block for each new password that you're trying if you're using a mask attack or a brute force attack on it. And when you reach the end of that, you can go back 1 block and recalculate it, or depending on your space and time trade-off, you just recalculate from the beginning. So we've successfully taken their nice, complicated, look at how many MD5s we have to do, and we've reduced it to a single MD5 block on average. This is not good. And so I guess my takeaway from these 2 examples is really, if you don't understand, and I think everyone in this room knows this, but if you don't understand how attackers go about attacking algorithms, please don't go writing algorithms from scratch. If you know any developers who are trying to write their own algorithms, please tell them to stop. The good default answer is use decrypt or just use something that someone else has invented that's been tested. I'd like to talk for a little bit now on some of the old algorithms. And I've implemented some of these relatively recently because they're kind of interesting and they're really very different. The 2 that, well actually the 3 that really come across as interesting are the SAP-D and SAP-G algorithms going by their John River names, and then SunMD5. So these were password storage algorithms that were written at a very different time. And you can tell this when you go about implementing them because they just feel very different. One of the things that both of the SAP algorithms use is the concept of hashing your initial data and then using that initial hash to drive some really very weird operations where you're pulling data out of a magic table or you're incrementing based on the value of bits. It's really a very bizarre operation, and unfortunately, it doesn't parallelize very well on GPUs. So, data-dependent branching is something that I think we've gotten away from with password storage algorithms, and I'm not entirely convinced that that's a good thing. Because our new algorithms are taking the concept of you do the exact same thing to different data with the exact same steps, exact same lengths, and everything else. Video cards are really very good at that. They're not very good at things that differ from one another. And then the other interesting algorithm is SunMD5, and I haven't been able to find the mailing list post that I think I read a long time ago that basically the author was saying, yeah, we don't really know what we're doing with this, so we just threw in the kitchen sink. But SunMD5 actually holds up very well because in addition to data-dependent branching, where there's the concept of a coin flip based on the output of the hash, you do one thing or another, they also decided that that a password algorithm really needed something a little extra. And so, I kid you not, this passage from, I believe it's Hamlet, is actually part of the password algorithm. They're just like, we need some data to shove through it because shoving more data through MD5 is better, so we're just going to use Hamlet. And what's frightening is it actually works really well. MD5 is not a fast algorithm. So yeah, I guess think about the old ways and think about data divergence and code path divergence and all that other stuff. It really doesn't hurt at all if you're doing one hash at a time, but it really hurts the attacker who is doing a lot of hashes at once. And finally, mostly because Pear requested, I wanted to go down a totally different path and look at some online cracking defenses. And I know that, wherever Tom is, the online cracking is not really quite as exciting, but it's still very effective. And so what I want to do is propose a system for defense against online password cracking attempts. And I want all of you to think about it and tell me why it's a stupid idea and why I shouldn't implement it, so I can fix what's wrong with it. This also ties neatly into the concept of preventing an attacker from overflowing your password hashing algorithm, or from creating a denial of service through your password hashing algorithm. One thing that's been brought up as a complaint about using expensive algorithms is, well, then the attacker can just submit a whole lot of login requests and DOS the server, and this is not good, so we should keep using plain MD5 because maybe our database won't get dumped. So my proposed system is to use Memcache as the backing store for this data, primarily because Memcache is fast, it's commonly available in web environments, and there's interfaces to it from pretty much every language. And what I propose doing is, if a specific IP address fails its login attempt, we add that IP address to Memcache and we increment a counter based on it with the Memcache atomic operations. If a username fails its login request, we add that and we put a counter on it. And then for each login attempt, we do a quick check and say, hey, based on the Memcache things, is this IP address or is this username exceeding their login limits? And if so, we don't even bother doing the password hashing function. We just say, I'm sorry, this doesn't work, and tell them no. So the threat model that I'm looking at here is sort of the typical brute force attacks. They're coming from one of multiple places. They're either coming from a single IP address, and as Tom mentioned earlier, it's doing a whole bunch of passwords for one user tends to lock that user out. Doing a whole bunch of users for one password currently doesn't get caught. Now, if you're coming from the same IP address, this system will catch that. It'll go, I don't know what you're doing, but your IP is failing a lot. You're probably up to no good. Go away. And then you also catch if somebody's using a botnet and 10,000 nodes to attack a single username, you also catch that and you prevent the attacker from coming in. So I'm sure there's ways around this. I would appreciate it if you could tell me about them when you think of them. I've seen things have already been found. So that ends my main presentation. Questions?
IPv6 and botnets on many people.
There's no difference against botnets, that kind of thing.
Yeah.
Like botnets with a whole bunch of IP addresses, or?
Yeah. If each bot attacks a different user, then you wouldn't detect it.
Sure, but now we've forced the attacker to have a single bot per user, which is a whole lot better than where we are today.
Also, with IPv6, you should probably just take the
Yeah, that makes sense. Anything else?
So we in fact use a similar system. It's not memcached, but it's a UDP based, ephemeral storage database for DOS mitigation on any kind of expensive operations, not just the hashing stuff. So I mean, this is a relatively standard practice, and I think you're right on track to worry about the ability to DOS a user specifically, in addition to DOSing your CPUs that you can do actual computations. But you also have to worry about things like, is memcached is its internal lookup function going to leak timing information?
Well, so I've already accepted that you leak some timing information with not performing an expensive hash function. But you can't keep all the attackers out.
You just sleep,
Well, true, but then you run threat pool exhaustion.
Use Node.js's web scale.
Is it also enterprise quality?
I also think it's a good idea, but of course you are replacing one sort of DOS scenario with another sort of DOS scenario. If you want to intentionally lock something out, that's quite easy.
Sure, but you can already do that.
What I like about your scenario is that, and I don't know if you've already mentioned this, but that once they exceed the limits, they just start getting no's. They could be getting no's for correct guesses.
Right.
And the correct guesses go into how things are.
Right. The idea is to identify the attackers specifically.
But they can also check that. They can check the timing of response. If the response takes, let's pretend 5 seconds for legit responses, and all of a sudden it just drops to 0. Because no isn't even coming back, maybe they know they're getting focused answers, and that further complicated.
Sure.
Guys, last one down in the corner, and questions, not discussions. Question.
What do you think about using SRP and having the attacker have to calculate the verifier every time?
I don't know enough about that algorithm to have an answer.
The secure remote password protocol?
I don't know enough about that algorithm other than it exists.
That's just for your password. You would send your username separately, which is what he's just out.
Okay.
Okay, well, we're done on that one.